Hello, in this video we will discuss strain energy in simple tension and compression. This is a prismatic bar subjected to a gradually applied load. If you plot a diagram between load and deflection, you will get a curve like this. During this application of load, at a particular moment when load is P dash, deflection is delta dash. So I have applied a load P dash here, and this beam is already deflected by an amount of delta dash. Now suppose if this load P is increased by a small amount, this will further get deflected, and this deflection here I have shown P dash is increased slightly, so deflection is increased from delta dash to d delta dash. So during this deformation or during this deflection, this P is moving from this position to this position. That means this P dash is moving from delta dash to d delta dash. Therefore, this P dash does a positive work, and this positive work stored in this bar as static energy, which is called strain energy. Now this work done because of P dash is moving by an amount of d delta dash. So work done by P dash can be given by P dash into d delta dash, and this work done P dash d delta dash. Here in this diagram you can see this area is P dash into d delta dash. This area is the P dash into d delta dash. Therefore, if you integrate, then total strain energy can be calculated. So if P is applied up to here, then you have to integrate from 0 to del. You will get this total strain energy. If you remove this load after this, if you remove this load P at this position, stress will become 0, but there will be some permanent strain. Up to here, that means up to elastic limit, if you remove the load, the entire energy will be recovered and this bar will regain its original position. So what is strain energy? Strain energy is the increase in energy associated with the deformation of the member. So we are considering here the linear portion of the curve. If you apply a load P gradually, then you will get a deformation del here. Now in this case, the strain energy stored in this bar is equal to area under this curve. That means area, this triangular area, and this triangular area can be easily calculated by the relation half P into del. The area of triangle is half base into height. So base is del and height is P. Now you can get different forms of this strain energy relation by eliminating either P or del. So we know that del is equal to PL upon AE. In this equation, half P into del, you can eliminate either P or del. So first I am eliminating del by putting value of del as PL by AE. You will get a relation P square L upon 2 AE. So this is the most common expression for determining strain energy in simple tension and compression. You can eliminate P also, then you will get relation as AE del square divided by 2L. Now another term, the strain energy stored by the body within elastic limit is called resilience. So this area or this work done or this strain energy is called resilience. So this is the maximum energy during elastic limit. This is the maximum load that you can apply. During that time, the energy stored will be this area, and this energy stored is called proof resilience. To eliminate effect of dimensions of the bar and only consider properties of material, we use another expression, that is strain energy per unit volume. So this is U divided by V. So in this case, this prismatic bar, volume of this prismatic bar can be calculated by cross-sectional area into its length. So A into L is volume. So if you divide this expression with AL, you are getting this relation P dash d delta dash divided by AL. Now P dash divided by A is the instantaneous stress and delta dash divided by L is the strain. You can rewrite this expression as U by V is equal to small u. I am representing strain energy per unit volume as small u is equal to integration 0 to epsilon sigma into d epsilon. That is, sigma is stress and epsilon is strain. Now from this expression you can see that P dash into d delta dash and its integration is the area under this curve, that is load and deflection curve. So sigma into d epsilon will also be area under the curve, but in stress strain diagram. So if you draw stress strain diagram, then area under the curve will be this expression. Now area under the stress strain diagram when stressed up to rupture point, that is at the maximum point, if you stressed, if the body is stressed up to this point, then the area under the curve, that is total work done, that is strain energy per unit volume up to rupture point, is called modulus of toughness of the material. Stress strain diagram up to yield point, if it is stressed up to yield point, then that work done, that is area under the curve or strain energy per unit volume in this particular case, is called modulus of resilience. So modulus of resilience is the energy per unit volume that the material can absorb without yielding. We can get expression for strain energy per unit volume in different forms. As we have get AE del square upon 2L. So one expression for strain energy is this one. One expression for strain energy is this one. So from this you can get divided by AL. U by V is equal to divided by AL. If you simplify this, you are getting E epsilon square divided by 2. So E is Young's modulus, epsilon is strain square divided by 2. So this is strain energy per unit volume. Strain energy per unit volume can also be represented in this form, divided by AL. So what you will get, sigma square divided by 2E, that is stress square divided by 2 into Young's modulus. Also you can represent in terms of both sigma and epsilon. Strain energy per unit volume will be sigma epsilon divided by strain energy by impact loading. Suppose a load W is dropped from a height of h on this bar. So because of this impact, if no energy is dissipated and this bar remains within elastic limit, then the total work done by this load will be W h plus del. Total distance traveled by W is h plus del. So work done is W h plus del. So this work will be stored in this bar. So therefore you can equate this WH plus del into any one expression of the strain energy. So these different expressions I can show here. So these are the different expressions of strain energy. You can equate this WH plus del with any of these as per requirement. Now at this particular moment I am equating this H plus del into AE del square by 2L. So WH plus del is equal to AE del square upon 2L. Now you can simplify this. Now 2L and AE I brought it here. So 2WL upon AE H plus del is equal to del square. Now WL upon AE is the deformation or elongation of this bar when this load W is gradually applied on this bar. So if W is applied gradually on this bar, then its deformation will be WL upon AE. So this deformation I am representing as del ST, del static, which is equal to WL upon AE. So I am replacing WL upon AE by del ST. After replacing and simplifying, you are getting this quadratic equation. So from this quadratic equation, you can get the value of del. So this is 2 minus b plus minus root over b square minus 4ac upon 2a. From this relation, I have taken only positive because definitely this WST static deflection will always be less than del, and therefore it must be positive. This term should be positive, then only you will get del greater than del ST. So this is what you are getting, deflection of this bar in terms of static deflection of this bar under this load W. Now there is another case for sudden application of load. If this load is not applied gradually, instead it is applied sudden, then you can, in this particular expression, you can replace this h, or you can put this value h as equal to 0. So you are not dropping the weight, but instead you are keeping this W directly or suddenly. In that case, what happens? This h will become 0 and the deformation del you are getting is equal to 2 times del ST. Now what is del ST? Del ST is the deformation or deflection of the bar under this load when load is applied gradually. But if load is applied sudden, then in that case deflection will be double the static deflection, and therefore strain due to suddenly applied load is double that of gradually applied load. Evidently the instantaneous stress will also be double. So So in case of suddenly applied load, stress and strain are double compared to what when load is applied gradually. Now we will solve one problem on strain energy. This problem I have taken from the book of Rajput. So you can see that two similar bars A and B are each 30 centimeter long as shown in figure. So these two bars A and this is another bar B, and this bar A receives an axial blow hitting this bar. It is getting one axial blow here, which produces a maximum stress of 200 meganewton per meter square. We have to find maximum stress produced by the same blow on the bar B. If the bar B is stressed to 200 meganewton per meter square, this is second part of the question. If bar B is stressed to 200 meganewton per meter square, determine the ratio of energy stored by the bars A and B. Now here first axial blow in A and B both are equivalent. That means strain energy stored by this bar and strain energy stored by this bar will be same. So what we have to do, we have to calculate strain energy in this bar and strain energy in this bar, and we have to equate those two strain energies. So now it is given that maximum stress of 200 meganewton per meter square in bar A. Now bar A has two portions, one is of 2 centimeter diameter, one is of 4 centimeter diameter. So stress will be maximum in 2 centimeter diameter portion. So you have to consider stress in this portion. What are the values given? A1 is equal to pi by 4 2 square into 10 raised to minus 4. This is in meter square. And A2 is also pi by 4 4 square 10 raised to minus 4 meter square. I have not written unit here, so you can write that unit. Now I am considering one equivalent load on this A. That means because of blow this get deformed. So the same deformation you will get with one gradually applied load. That gradually applied load I am assuming as P into EA. So if you apply this PEA, you will get the same deformation as obtained by this axial blow. So now we know that this applied load is equal to sigma into A. So this portion, we know this portion value of sigma in this particular portion is given 200 meganewton per meter square. Therefore I am taking this portion. So sigma 1A, sigma 1 in this portion multiply by cross sectional area of this portion is equal to PEA. Similarly, I am assuming another value PEB, which is gradually applied load on B, which will produce the same deformation as produced by the axial blow. So this PEB is equal to, again I can take any of these two portions. So I am taking this portion so that I should get maximum value of sigma. So sigma at this portion into area in this portion. So sigma 1b into A1. Now strain energy expression, we know that P square L upon 2AE. So in that expression it has now this bar and both bars are having two portions. So strain energy can be calculated in two parts. So UA is equal to P square L of this part, strain energy in this part and strain energy in this part. Now this applied P will be same in both the sections. So P square is same, P square into L, length of this portion is 10 centimeter, 0.1 meter, divided by 2 into A1E. So this area is A1 and material is same, so I am taking it as E. For second portion, for this portion of bar A, P square into 0.2, this length of this portion is 0.2 meter, divided by 2 into A2E. So you can take it out, P square upon E is you have taken out 0.1 upon A1 plus 0.2 upon A2. Now UB, for this particular case, you can see that this length is 0.2 meter. So P square L divided by 2 A1E, and P square L here in this case it is 0.1 meter. So 2 A2E. So you are getting P square B divided by 2E and 0.2 upon A1 plus 0.1 upon A2. Now equate these two. So here you can see that 2E and 2E are same. So you can eliminate this 2E and 2E, you can cancel out. So cross multiply this. So 0.1 into A2 and 0.2 into A1, 0.2 into A1. So in denominator you will get A1 into A2. Similarly here also multiply here 0.2 A2, 0.2 A2 and 0.1 A1, 0.1 A1. In denominator you will get again A1 into A2. So A1 A2 here and A1 A2 here both will get cancelled. So finally you will get this expression P square A 0.1A2 plus 0.2A1 is equal to P square B 0.2A2 plus 0.1A1. So now you can put these values of P square is this into A1, 200 into 10 raised to 6 into A1 square, this is P square, and this same value, this same expression, then this P square EB is sigma 1 into A1 square, so 0.2A2, and this same value, this same expression. Here A1 square and A1 square, this also get cancelled, so sigma 1B you can calculate. I can write sigma 1B square, so sigma 1B square is equal to this expression, this expression, these two divided by this part, this expression, so 0.2A2 plus 0.1A1. So here now you can put values of A2 and A1, so this is A2 and A1. In both A2 and A1, this term pi by 4 10 raised to minus 4, pi by 4 10 raised to minus 4 is common. So I put only values 2 square for A1 and 4 square for A2, because this will get cancelled in numerator and denominator. Both you will get A1, A2, A1, A2, both will get cancelled. So I am writing these values here. So this is 200 into 10 raised to 6 square 0.1. So in place of A2 I am writing only 4 square, that is 16, and 0.2 into A1, that is 2 square 4. So similarly here in place of A2 4 square, and in place of A1 2 square. If you solve this, what you will get? This is 1.6, 4 square into 1, this is 0.8, and this is 3.2 plus 0.4. So you are getting this term only. I am calculating this 1.6 plus 0.8 divided by 3.2 plus 0.4. This is what you are getting, 0.666. So this is sigma 1b square, so you get its root. So sigma 1b is equal to, if you take root, this 200 into 10 raised to 6 is same, so 0.816, its root is 0.816. So 0.816 into 200 is 163.22, and 10 raised to 6 is mega Newton per meter square. This is the stress which you will get in this portion of the bar B. Now in second case, find maximum stress produced by the same blow on the bar. Okay, second part is if the bar B is stressed to 200 meganewton. Now this sigma 1B is given 200 meganewton meter square. So we have to determine the ratio of energy stored by the bars A and B. Now this term and this term which we have come across just now, these two are proportional to strain energy of A and strain energy of B. Other values are same. Therefore, if you take ratio of U and UB, those terms will get cancelled. That's why I have not written those terms. Only you will get this part. So UA and divided by UB, you can write this. A1 is same, A2 to same values what we have calculated before. So UA divided by UB, so this term divided by this term. So 210 raised to 6 square. So A1 and A1 both are same, so get cancelled. And this portion is 1.6, which we have already calculated. This value is 1.6 and this value is 0.8, and this value is 0.4 and this value is 3.2. So in this way we have calculated already these values we have already calculated. When you solve this, you will get 2 by 3. In this way strain energy ratio can also be calculated. Now let's go to second problem. In this second problem, an unknown weight falls through a height of 10 mm on a collar rigidly attached to the lower end of the vertical bar, 5 meter long and 600 mm square in section. If the maximum extension of the rod is to be 2 mm, what is the corresponding stress and magnitude of the unknown weight? Take modulus of elasticity E is equal to 200 giganewton per meter square. Given values are length 5 meter, this length is 5 meter, cross sectional area is 600 into 10 raised to minus 6 meter square. So I have converted mm square into meter square. Value of E is given, height is 10 mm, so 10 into 10 raised to minus 3 meter, and del is given 2 into 10 raised to minus 3 meter. First we will assume an equivalent load as WE, which when applied gradually on this bar will produce same deflection as produced by this falling load. So WE is definitely WE will be greater than W, so that it will produce the same deflection. Now we know that from deflection formula del is equal to WEL divided by AE. So here all these values are known. So this equivalent load we can calculate. Equivalent load is equal to del AE divided by L. I have put all these values here divided by 5. Then you will get 48,000 Newton as WE. Once you get this equivalent load, you can determine stress. Stress is load divided by area. So you can calculate stress as equivalent load divided by area. So area is given 600 into 10 raised to minus 6. By calculating this, you are getting 80 meganewton per meter square. Now remaining is this weight. When this weight falls, it travels a total distance of h plus del. So work done by this weight is W into h plus del. Now this same work is obtained from this gradually applied load. Since this load is gradually applied, therefore work done by this load is half of WE into del. So equate these two. By equating these two, you can determine value of W because all other values are known. So from this, W is equal to half WE equivalent load, which is 48,000 Newton. Put this value here and put value of del and HH. So you will be getting 4,000 Newton as weight of this falling load. Now a prismatic bar of length L and cross-sectional area A hangs vertically under its own weight. How much strain energy is stored in the bar if its weight per unit volume is gamma? I have given this expression for strain energy. U is equal to P square L upon 2AE. Now this relation is actually valid when this P is constant throughout. If this P is changing or varying at different sections, at that case you have to determine strain energy by this relation. So in place of P, this P is variable. So Px square. So at any section x, the value of P will be Px. And this length, in place of length, you have to take a small length element, that is length of that element is dx, and 2AE. And when you integrate this from 0 to L, then you are getting this strain energy. Self load, you can see that self load at this section will be 0, and at this section will be weight of this entire bar. So in between, this weight is varying. So in this section there is no load acting. In this section some load. In this section maximum load is acting, which is equal to weight of this particular bar. So what I will do, I will take one small element of length dx, a small element of length dx at a distance from the bottom as x. So at x distance I have taken one element of length dx. Now in this dx, the load acting is the weight of this portion of the bar. So what is the weight of this portion of the bar? So volume into weight. So weight per unit volume is given gamma. So if you calculate volume of this part of the bar, then multiply it with gamma, then you will get weight of this portion of the bar. So Px is equal to, so you can write Px at this point, load applied is gamma into A into x. So cross sectional area A into this length x is the weight of this bar. Weight is the applied load P. So now put this value here and integrate. So if you put this value here and integrate, you will get gamma square A. So this is constant, all this constant, you take them out. So x square by dx, when you integrate, you will get gamma square AL cube divided by 6C. This is what you will get as strain energy of this bar. In this way, you can calculate strain energy in tension and compression. In next videos, we will discuss strain energy because of torsion and bending moment. Thank you for watching this video.